And yes, I am so happy to have Dean Peterson with us today. So Dean is the Chief Geologist at Big Rock Exploration, and his 35 plus year career in North America includes stints in government, research and teaching, and industry. He's spent decades of work in Mafic Magmatic Systems in the Duluth Complex, Sudbury, and Antarctica. So it is going to be amazing learning from him today about understanding Mafic Magmatic Systems, views of the Ferrar Dolerites of Antarctica, and Cu-Ni-Co-PGE bearing Troctolites in the Duluth Complex. So strap yourselves in. It is going to be an amazing session. Please keep using the chat and we'll open up the floor at the end. And yes, thank you so much, Dean, for joining us today. It's awesome having you.
Okay, I just want to start off first by telling everybody I am not an igneous petrologist. Just so you know, I muck around with them a little bit, but I'm very much an economic geologist. Spent most of my career mapping. So a lot of the work I've done, I've published all kinds of geology maps over the decades, and spent years of my life in a tent, kind of thing. So that's kind of what. Yeah, I just want to start with that. So, and kind of also what I'm talking about today is just kind of understanding these systems, how you can, get a handle on it from the beginning, so you actually know what you're looking at. Because there's too many companies, from my work out in the field, too many companies, and there's projects that all you can do is look at core, and it's really hard to look at core and understand it in this system, this magmatic type, because the minerals are all the same and it's different proportions, even different chemistries of them. When you see it weathered, you see something different. So that's when the really insights come out. So just want to say that. And for today's geohug, I have a forward-looking statement, which I'll let you read it, but one thing I'm going to do here is kind of questioning dogma that there's out there for sure in all kinds of systems. I'll talk about a lot of things and maybe some new ideas you haven't heard about before, but there are people who are smarter than me in this realm, and I reserve the right to change my opinion if there's new information that comes up, or even in the chat in the end here. So just want you all to know that. So, a lot of what we do, a lot of you probably are also doing it, exploration by the mineral systems. And I have just some stuff here in the bottom, kind of mid-continent rift things. I'm not going to go into that at all right now, but what we have to do when we think of Mafic Magmatic Systems is just, think about, what these systems do. They focus mass and transfer energy. So we see that by, the masses, the intrusions and the different crystals and so on in it, and the energy transfer. We can see many ways. You can see the chemical transfer of energy by melting things. We can see thermal transfer of energy by, baking, or melting kind of country rocks. And I have a slide on this, but one of the main kind of energy things we see in these systems is just momentum. And I'll have a good slide on that, of how, when magmas intrude, they go faster in the center than they do on the edge. And that makes huge impacts to the outcome of what we actually see as geologists in the end. So outline of this talk, it's kind of a combo platter kind of thing. It's, there's about aspects of about 4 or 5 different talks in here, that I'm just gonna, touch on, a little bit about me, who the world I am, right? A few fundamentals on, forming mafic magmatic ores of nickel, copper, cobalt, PGE, just some like nice views of Antarctica, and then going into mafic intrusion ore deposits. And, the Ferrar Dolerites of Antarctica, spent 2 seasons down there, camping, unlimited helicopter time, and never saw a sulfide mineral at all. This was not about finding ore deposits down there. It was understanding these systems. And it's an end member system, which I'll talk about. And then this kind of, the things I learned there, I applied to the Duluth Complex to come up with a whole new understanding of what those ore deposits are. And it changed what we think of that, we'll just say that. And I've done a bit of geology in North America. All these dots are various research project, mapping project, exploration projects. I've done, a bunch in Alaska, a whole bunch around, mid-continent, kind of Precambrian geology, granite greenstones and so on, and a whole bunch of stuff out west. A few areas in southeast U.S., we'll say, got chased by cottonmouth snakes in Georgia, and I haven't been back there again. And with all that, if we look at the slide, I have Dunning-Kruger effect, which is a slide I really like to put in talks on the, it's confidence versus wisdom. And I can tell you all, and I'm sure every geologist who knows what they're doing have climbed the peak of Mount Stupid. They think they know what's going on, and then they fall into the valley of despair because you're wrong, right? So hopefully we can all end up in somewhere up here where you have confidence and you have wisdom of what you're looking at kind of in the end. So the mineral systems I've worked on, mostly in generative exploration, that's kind of what I've done, right? And research, and the research I've done at University of Minnesota System has mostly been on generating exploration targets kind of thing. And a lot of, mapping, publishing maps too, but orogenic gold kind of all over North America, magmatic systems, Jessica said, Minnesota, Duluth Complex, Sudbury, Ontario, Antarctica, VMS deposits in Minnesota, Alaska, porphyry copper. I'm the guy who mapped Pebble in Alaska back 25 years ago. Epithermal gold, there's like Pebble-related deposits around that. Spodumene pegmatites in South Dakota. Just finishing a project on lithium-rich clays in Nevada, Clayton, kind of manganiferous iron formations in Minnesota. That's the kind of stuff I've been working on. There's others too, but that's the main thing. Kind of just your classic mineral restoration triangle. Not going to go through this, but this talk is about the lower right, the intuitive thought that, which is how projects start, kind of thing. Is like, where's the idea coming from that there might be something here? And in these kind of Mafic systems, it's it's understanding that system is how you actually come up with the intuitive thought. It's like, yeah, there might be ore here, there might be ore there, or here, or this is the kind of thing. So this is really what my talk is about. It's just this bottom right corner, and you can come up with intuitive thoughts of where our company should spend money exploring for copper or gold or nickel or whatever it is, by looking at geology maps, creating new geology maps, doing geologic research on something, or reading the scientific literature. It's like, oh, look at that. It's always really important, at least in my opinion, to have geology maps up on the wall in your office, right? And a whole bunch of them, and just keep walking by them, because sometimes all of a sudden the light bulb will go off in your mind. Oh, look at that thing right there, right? So, okay, I'm going on from there. We look at kind of magmatic systems. The first principles that you must kind of address are the initial conditions. What was this area like before there was some intrusion? Okay, that's one thing. How did this intrusion form? That's what we're talking about today. And it's not an easy thing to ascertain. Nobody's been inside of magma except Gollum, right? And in the Lord of the Rings, right? It's like, I've never been inside one, so we don't really know exactly what it is. But the things you have to think about is the timing of magma injections, and in this ore deposit type, when did sulfide saturation take place? The mode of delivery of volumes of magma, was it episodic? Was it just a slow progression? Was it very aggressive? That it's just a voluminous, here you go, and then it slows down, and then again and again. So voluminous things are where you form ore deposits, at least in my opinion. The concentration of phenocrysts and what phenocrysts can do, that's going to be a huge part of my talk, is that right there. But perhaps the most revealing means of understanding magmatic systems is to examine and usually complete well-exposed systems, where the initial conditions are clear, and there's really two end members of this ore deposit type. There's Sudbury, which I'm not going to really talk about today. I have a slide which I'll put the highlights, Yeah, it was a meteorite impact. It was an impact melt sheet, superheated thing. You formed a whole bunch of nickel deposits there. We know that. The other end member is Ferrar Dolerites of the Dry Valleys of Antarctica. These are intrusions of just phenocryst laden magmas that just form all kinds of rocks that you would not imagine you could form in a system like this. It's all from the same basaltic liquid kind of thing. And we'll look at what we form from a system like that today. But if we think of any sort of mafic intrusion, here's where it all kinds of begins. All intrusions, not just mafic, they start the size of this dot. They start smaller than that. And there are intrusions that are, Duluth Complex, South Kawishiwi is probably, I don't know, 6, 7, 8,000 cubic kilometers. That's how big it is, and that's it's eroded too. It's like, how did you fill that thing with magma? And that's a hard thing to ascertain. And I mean, I remember when I was in college. This is like in the '80s, right? Early '80s. We were just taught that, okay, you fill this thing with magma, and then what happens? That's how we think about mafic intrusions, and didn't think about how'd you fill it, and all of that. So this is always a starting point. Just always remember that your intrusion started with nothing, and now it's in front of your eyes, or below your feet, or whatever it is. And there's 3 main kind of boundary conditions that when we think about this, these ore deposit types, you have to deal with. And these are first principles. These are boundary conditions that all kind of intrusions have, especially the mafic ones, because they're way less viscous than the granitic one. But the boundaries there's chemical boundaries. You have a phenocryst, or not a phenocryst, an otolith, or just a country rock fragment, and you see chemical boundaries around that from the magma, and they're generally measured in centimeters, kind of thing, unless you're wholesale melting things that you can really change the chemistry of the intrusion. But a lot of what you really see are just within centimeters. There's thermal boundaries within these things, and I'll show you examples in my talk here. That thermal boundaries can be, tens of meters, 100 meters, but in other places it's less than a meter, where this is hot, country rock's cold, and you have this boundary, this thermal boundary, where you might have pyroxene hornfels or something. But the main kind of boundary condition in a mafic system is momentum, where the magma flows a lot faster in the center than it does in the edge. And that induces essentially shearing within that magma, magmatic shear zones. And so in effect, thin thermal and chemical boundary layers are embedded in wide magma flow induced shear zones, where variation in velocity is broad and gentle. I've been told, and I know I've done this, given talks where I kind of dance across the floor, just do this kind of thing, because that's what these systems do. So the magma is moving a lot faster right here than it is right there. That induced shear in here. That would be sinistral shear going on in there. So things can happen along those shear boundaries. There's just in core, you can't really see this, but you can see these, there's olivine is coming up like that. And then there's essentially schlieren of really fine grained plagioclase in here. And here's a boundary. This is a granular troctolite right here. It was probably almost solidified. And then this flowed on top of it. So just something to think about. And I clearly was taught this, that, how do you form a layered intrusion? Well, you have crystals nucleate in the center of a magma chamber, and they fall to the bottom to form a layer. I think, I've worked with Bruce Marsh in Antarctica, and I put a big red X on this now. This is not how it works, because intrusions solidify from their boundaries in along the solidification fronts. We're taught about the solidus and the liquidus. These are, we're taught in college that they're like these graphs that we deal with, right? But they're actually 3-dimensional surfaces that move in time. And if you're nucleating crystals on the edge, these are like nanoparticle crystal size. If some particle falls, goes into the magma, it just dissolves back in. So you really don't get this in these from what I know. Again, I'm not an igneous petrologist, but how do you form kind of crystal laden magmas? Phenocryst rich magmas. Well, you intrude things through solidifying magmas. So magma, crystal free magma might come in through a whole system. Below a volcano, we'll say you have an upper staging chamber, another staging chamber, another staging. If you have a voluminous something's going on in the mantle and you're rushing magma through there, it'll rip through this solidifying magma, which again would be you're going to rip through the solidifying parts of this and form phenocryst that could rise up to form phenocryst laden kind of lava flow or whatever. I mean, this kind of thing happened in Kilauea, Hawaii, 2 or 3 years ago. The initial phase of that eruption was taking actually a staging chamber up in here and dumping it out, and then it came directly from the mantle. And those later, we all saw the movies on YouTube of those rivers of lava just flowing down, right? They were going 40 miles an hour, and those are full of olivine phenocrysts. That's what that ended up in the end. And those phenocrysts are FO90, and they're coming from the mantle, right? They're just directly from the mantle on up into the lava flow. So, and why are phenocrysts important? They're really important because they can carry the entrained immiscible sulfides. And they can carry them for 10, 20, 30, 40, 50 kilometers and form an ore deposit, right? So it's like really, really important, if you're looking for a mafic system, the first thing I look for is there evidence that it was phenocryst rich. That's the first thing I look for, because then I know that magma could carry sulfide, and that sulfide can be moved somewhere and accumulated somewhere to form an ore deposit. If you really don't have the phenocryst in there, it really doesn't have the ability to move sulfide very far. Yeah, it can, happen in place right somewhere and form tiny little ore bodies, but you're not going to form massive, huge deposits, we'll say that. So, and a little bit of work with Jim Mungle, you can kind of read that, this is kind of a Duluth, it's a classic Duluth complex, kind of a copper, this is almost pure chalcopyrite in there. You can see the plage phenocryst in there. There's olivine phenocryst in there. It's all disseminated interstitial sulfide in there. And it doesn't go to the bottom because it's got all this stuff in the way, because that liquid sulfide sticks to crystals in there. And it can go for a long, long ways. And we can, think of, crystal-free magmas. Yes, you can form small ore bodies, with abundant barren waste rock, or you can form much, generally much lower grade, but huge tonnage, huge amounts of, metal in these systems. And there's really almost no waste rock in these things. Once you get into the ore zone of disseminated, it might be 0.5%, 1% copper, 0.2, 0.3 nickel, maybe a gram platinum palladium. That's your ore, and there's several billion tons of it, kind of thing. So kind of the end members, really not going to talk about Sudbury today. I'm going to talk a lot about the Ferrar Dolerites today. But here are the end members, Sudbury, impact melt sheet. The magma was superheated. So the magma, Sudbury igneous complex, formed in an instant, and it was superheated, 1,700 degrees C. There was not a single phenocryst or anything in that in the end, right? Because it's too hot. And what do you get in the end at Sudbury? You get, the mafic norite, felsic norite transition zone in the center. There's not a single layer of minerals. There's not a modal layer in the thing anywhere, right? It forms ore deposits, and they're beautiful things. That's a whole nother talk. I could talk about, convection, the 10 or 20 years of convecting to get from 1,700 degrees C to like 1150, and how that formed the ore bodies in the embayments kind of thing, because that's where the most heat was, because you had a thick, the footwall was a little bit deeper kind of thing. But the Ferrar Dolerites are just a classic continental rift, breakup of Gondwana land. There's no superheat in the system. I mean, these things are intruding at essentially the liquidus temperature, right? there's just a huge sludge of phenocrysts in there, mostly orthopyroxene phenocrysts, which we'll see that. And that thing can be layered like mad. It forms layered intrusions within a sill itself, when certain things happen. And the fundamental research, and I was down there in 2006 and 2008, 2 seasons down there, kind of about 6 weeks each, I guess. We're out camping in the Dry Valleys, essentially camping a bull pass camp right in the center of the orthopyroxene tongue of the basement sill, which we'll see pictures of this. It's actually a Gondwanaland breakup, thin the crust, melt the mantle, comes into the kind of shoulder of the rift. We see there about 4 kilometers of the crust there because the rocks are tilted, so we can see, as we go inland from Antarctica, we see higher and higher and higher through the crust there. And so, the basement sill is actually intruded in the basement of the Beacon Group sediments. These are kind of Devonian sediments. There's sandstones and coals in here, and this kind of stippled pattern in here. There's actually the Kirkpatrick flood basalts, which are related to the Ferrar Dolerites. On top, we've only seen a little tiny bit of it where we were working. But there's the upper Mount Fleming sill, the Asgard sill, and these are standard, I guess, as Australia, you would call them dolerites, and North America, we call them diabase. They're just dolerite diabase sills, and there's almost featureless. It's fine grain, at the margin, just, medium grain in the center, and then fine grain. There's really nothing. This was all liquid. This was all basaltic liquid that's solidified from top down, bottom up, and so on. Asgard sill, pretty much the same way. Peneplain sill and the basement sill in certain areas, have a slug of phenocrysts where the intruding from depth was incredibly aggressive. It was a huge impulse of magma that we were ripping up all kinds of phenocrysts from solidifying chambers at depth. And this is kind of what we're going to be looking at today to see, several things. How do you make a layered intrusion is one, and just what do these things look like? Kind of thing. Just, Antarctic acknowledgements. And I went with Bruce Marsh from Johns Hopkins University and his grad students kind of thing. I was one of the first kind of, I'm clearly not his peer in his metrology, but, older, been around the block. He hired me because I could map these rocks kind of thing. And also, when you go to Antarctica, the support staff at McMurdo, Raytheon, the helicopter pilots, National Science Foundation, where I was working at the time, University of Minnesota, Natural Resources Research Institute. You don't often see views like this. Taylor Glacier, Ferrar Glacier, there's the boundary of 2 glaciers coming out of the East Antarctica ice, polar ice cap up here, going down these valleys toward the Ross Sea there. Mount Erebus, 13,500 foot volcano, active volcano. This is where you do snow school. You have to start out when you go down to Antarctica and sleep overnight in the ice shelf and build yourself it's almost like a coffin under the ice. You can sleep, so you know how to deal with cold, we'll say. And you're in Antarctica when you see penguin tracks. I don't see these in Duluth really very often, we'll say. Kind of like my little bit of experience in Fremantle and Perth, and kind of vacation thing out there, and then going north to I can't remember what the name of it. Walking out in the bush there and seeing emu tracks, that was pretty interesting for me too. So a couple more Antarctic views. We're up high in the helicopter, 11,000 feet, kind of looking west, or 5 miles west of Mount Fleming, which I'll show you on a map in a minute here. And this is the ice sheet. This is what it looks like. It's 800 miles to the South Pole, and you're just going up, 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 up. And if you turn around from here, and go 5 miles and turn around and land on top of Mount Fleming, this is what it looks like. So the Ferrar Dolerites are actually keeping the ice at bay because they're resistant to erosion. So they kept this area ice-free, essentially, for a long time. So that's why we can see everything we can see in here. It was 95 degrees Fahrenheit below wind chill at this moment. And we just jumped out and took a picture. And again, if you haven't bathed for a month, this is what happens to your hair, kind of thing. So but you know, maybe my last Antarctic view, and one thing, especially if there's young people listening to this, if you ever get the opportunity to do work in an area like the Arctic or the Antarctic or wherever it is that has 100% exposure, just take the opportunity because it blows your mind to actually see everything. Spent most of my career in kind of the boreal forests of northern Minnesota and Ontario. You know, there's trees and shrubbery and bugs everywhere. And an outcrop is like a find, right? You know, it's like, oh, look at that. You know, here is total outcrop and we can see everything. This is actually the basement sill of just one small tongue of the basement sill here. It's fine grained in here, you know, chilled margin. This sandy looking area we can see in here, that's the orthopyroxene tongue. So that is a slug of orthopyroxene phenocryst within this system. And it weathers out as orthopyroxene sand right there, essentially. It's all granite, but there, peneplating sills up on top of here. But these are actually columns. These things we're seeing here, columns are about 10 meters across. I don't know how tall they are. They're big, giant column. You know. So this is kind of what we started at here. This is about 115 kilometers right here. This is essentially where we started. You know, in 2 seasons to end up making a geology map. That was kind of what I was doing with Bruce. He was doing a lot more of the research on the chemistry of the sills and so on. You know, trying to put it all together in 3D and everything. We did our camping in Bull Pass, which is this kind of northwesterly trending valley between Wright Valley and Victoria Valley here, Taylor Valley there, Ferrar Glacier right here. This is actually where Scott went up to try to go to the South Pole in 1905. And they actually got up to the top the first time and turned around because it was like they got up here with ponies and you know, it's 800 miles to the South Pole and they knew they couldn't make it, so they went back down. So a geology map, just so you know, contour interval in that map is 200 meters, which is, you know, more than what I'm used to. So my job was to, you know, sketch geology and go check it out, see if it's correct. Because, you know, once you have some experience there, you can see all the rock types. We're not doing detailed geology, but it's this sill, that one, this one, that one. Here's the metamorphic rocks. Here's the beacon sediments, and so on. You know, just to make a geology map. Did it by, you know, landing. You get dropped off and landed here, and can map a huge area right here just by looking or walking and mapping it out. And they're just on field sheets, just kind of classic mapping right here. Land sketch geology on field maps, field check, repeat. Repeat, boom, 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 boom. And we ended up with a geology map in the end. And it kind of looks like this. You know, here's where we camped. We were just looking, you know, let me go back up. Our camp was right here in Bull Pass. That's this valley here. Here is this orthopyroxene, you know, slug in here, but in this thin sill on a geology map, that's this thing right here. It's very interesting. The sill goes along, you know, essentially horizontal. Then near its end, it goes up about 500-600 meters. Just it ends up being about a centimeter wide on top there. So it's like cutting through. Very interesting kind of thing. So I have, you know, this is Jessica put this up on kind of LinkedIn. We're just going to go through a few slides to look at what one of these, you know, at least the basement sill system looks like, you know, from, okay, the magma, you know, we mapped an area where it's coming straight up. You know, it's coming, we can stand there and you just look out in the field and go, it came from directly below us. And we'll see what these things are. We call them ring structures. They're really not described in literature. Hundreds and hundreds of these things. And we'll see what they look like. You see where magma comes up, it goes upwards right there. And it actually melts the hanging wall, multiple chilled margins, you know. There's one area that we mapped, there's 11 different chilled margins in it, where just effusive, you know, it's like it comes in, it's melting that, and then the system relaxes. Then it does it again and again and again. And most of the area that we map would be in this area right up in here, which are just classic slurry textures. Magmatic shearing going mad. It's just slurring, and you just can't believe it, right? You can walk on that all day, and you just at the end of that day, you just want to throw your textbooks away. And then in places you can add energy to the system, and by dropping maybe a kilometer or two, this magma's coming up, and now it drops down, and all that potential energy is converted into like real energy, and these crystals that are in here just sort like mad to form essentially a layered intrusion within a cell. And then that system rises up again, slurry reorganizes itself, and then just keeps going and going and going. Ferrar system goes for like 1,000 kilometers, if not more. And the last pictures are from way, way far away, where we're out of any sort of orthopyroxene slug. We're just in basaltic liquid coming out at the end. So the next few slides are like 1, 2, 3, 4, 5, way far away kind of thing. And just another little satellite view, camped here. There's that orthopyroxene slug in here. The ring structures were right in here. Magma came up, multiply, just melted granites like you can't believe. We got great pictures of that, and then just spread out hundreds of kilometers. And we go across Dry Valley to the other side, and we'll see what happens there, kind of thing. And these ring structures look like this, and there are literally hundreds of them. This is the brown you're seeing is all orthopyroxene, and it's maybe 1, 2, 3, 4 millimeters. That's the size of orthopyroxene. The white you're seeing is all incredibly fine-grained plagioclase, and these are vertical. They're subvertical Schlieren right here, and so we can just imagine magma coming straight up out of that, and we're just sorting the orthopyroxene from the plagioclase in there, forming these Schlieren of zones of incredibly fine-grained plagioclase, and then orthopyroxene phenocryst, and again and again. And these things are all over the place. So magma's coming vertically right out at you. And yeah, it's not perfectly vertical, but it's coming out. Above that, we're in this melt zone. This is granite right here, Ordovician granites right here. This is just actually almost looks like some column structures in here. These dark bands are all chill margins. So that magma came in, formed one chill margin here, ripped through that, formed another one there, ripped through that. And in places, there's kind of 11 of them. And here's what they look like in the field. There's Michael Zieg right there. There's a chill margin. It's actually quite contaminated. This is almost, it's got kind of, there's actually augite in these rocks in here. It's more of a dioritic kind of looking, contaminated, from norite to kind of diorite in there. And then here's another chill margin, another. Then a basement sill way off in the distance, and here peneplating sill way off in the distance there. We go up into the granites, did some mapping of this in here, and just sketch maps, kind of on field books. This is what we see. This is it's cooked granite, but it's also melted from granophyre here. Some of these have beautiful augite. It's almost spinifex augite in some of these. That's what it looks like. You get into the main part of the magmatic slurry, and it's Schlieren textures. And this is what you see everywhere. It's the brown, again, is orthopyroxene. The white is plagioclase. And you can go on and, what we're looking at is the magmatic shear zone right here, preserved. And these bands you see right here, those are areas where it was like active flowing along that. So we have earlier Schlier, the magma flow this way, and then it's cutting down through that way. So that's where we're getting kind of waves of movement of the magma and the kind of the momentum boundary that we talked about. So, I've been in a lot of places in the Duluth Complex where you see trough cross-bedding, and layered the base of intrusions. These are not trough cross-bedding, because that bedding, if you're doing cross-bedding here, it's topping that way, it's topping that way here. These are actually, that's just a zoom in right here. That's where we are, this picture right here. These are essentially magmatic shear zone, and you can see this perfectly in outcrop. Imagine a drill core through here. Would you see that? You wouldn't. At least I wouldn't, But if you see it in outcrop first, then you can see it in core, kind of thing. particle, segregation experiments. We had, back in the day, I was, employee of University of Minnesota Systems, so I had open access to the University of Minnesota's library, right, and all the online stuff, and would read all kinds of papers, right, And this is a very interesting one here. It's just about particle segregation. This is in actually the material science. It's not in geology kind of literature, but trying to mix two dissimilar granular materials, such as light and heavy or small and large particles, may lead to counterintuitive results. Putting more and more energy into mixing may result in more and more demixing. And we actually see this beautifully in Antarctica. And we see it right here. Those last few pictures were right along here. This classic slurry texture is going along in here. And then it goes from 6,744 feet elevation here to 900 feet down here. So that's dropping these in America more than a mile. So magma's moving and dropping down. You're adding a whole bunch of energy to that system by dropping that magma down, just under the influence of gravity. You can actually see layering coming on right here. That's what we're seeing down there. So we're just totally, absolutely sorting out the plagioclase from orthopyroxene down in here to form essentially a layered intrusion. And we actually mapped this thing out for 350 meters high from granite. It's not on this image right here, and just walked up and mapped exactly what we saw, and all different kinds of things, right? And I have thousands of photos from here, so I could do a whole talk on just dais if you really wanted to. It's very interesting, and things that we see in here, right? And it looks like this in the end. If you zoom in, again, this is weathering in Antarctica, so the wind is what's weathering. So every single rock is like a 3D exposure too, right? You can see under through it and kind of everything. So you get the whole thing. This is almost all plagioclase in here. This is almost all orthopyroxene in here. Here you can see a little, layering of orthopyroxene within the plage like that right there. So that's orthopyroxene and really fine grained plage. You come up to these outcrops, the first thing you think these are sandstone. It's incredibly fine grained plage in there, and kind of see it in here. This is, this would be a, orthoperoxenite kind of right here, a melanorite, whatever you want to call it. This is an orthosite right here, essentially. It's all coming from a basaltic liquid, right? The whole thing is. You get far away from these systems. This is the Fleming sill, Asgard sill is right up in here. And these are now mostly just liquid. We don't see any of these slurry textures, but we see a lot of action still going on. This is the Beacon Group sediments, whole seam right there in sandstone, essentially is what we're seeing in here. Incredible kind of, how do you make an intrusion? What's the cracking front right here? You can see this whole sequence of sedimentary rocks. Look at that thin little sliver of Devonian age rock. That was right on top of there, right? Drop that down. This is how you make an intrusion, and you just keep putting magma in here, and you're just lifting this thing out of the way. It can end up looking like that, right? Exactly how this fits. Does this go down somewhere in here? That piece is coming from there somehow. It's probably being warped and so on. It's just unbelievable, right? And it just kind of blows your mind, right? And there's huge sections of the Paleozoic strata. You have no idea where it went, right? It's like, I have no idea, right? And we always have problems with that, of things like that when we're out mapping, right? Something happened here where we're missing this, so we have to put a fault in there. It's like, no, you don't. It's gone. It's somewhere else. We don't know where it is, right? Especially when you don't have, you almost never have exposure like this. So you see something and you come up with, fits of fancy, right? I've done it myself, like probably hundreds of times when you don't know, right? You make an interpretation, but when you see what reality can be, it really changes your perspective on a lot of things. And this is a really good example of that right there. It's like, well, how the hell did that happen? I don't know, right? It's pretty cool, but when you get really far away, I told you before about 11, chilled margins. This is sandstone. You can walk up to this. This is just a Mount Fleming sill, and it's a long ways from the source now, probably 50 kilometers away, where we thought things were coming. At least the least the basement sill is coming from. You know, this rock is, the thermal boundary here is measured in like millimeters. Right? There's no metamorphism of this rock in here. This came in once and it chilled and you're done. Right? You know, so these are unmetamorphosed essentially right here. I mean, we would go back to some of the slides, they're metamorphosed long ways. Now this is kind of an awkward segue to my a few of my Duluth Complex stuff. You know, been around a long time, so I'm on my third field assistant dog right there. I had Bud, Dory, and Nemo now. So Nemo's with me here in Michigan. So, but you know, we look at the Duluth complex, and what do we see? We see phenocrysts everywhere. Plagioclase phenocryst, olivine phenocryst. That's what we see. There's a nice big, you know, Sharpie mark, you know, plagioclase phenocryst in a medium grain kind of anorthositic troctolite. That's all olivine, 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 olivine. All the rest is clad. It's a little really dark stuff here. Might be a little magnetite in there. It's probably magnetite right there. But there's almost no piercing. This is a anorthositic troctolite right there. Just classic rock. Mid-continent rift, one of the largest mafic systems on Earth. Yeah, here's the Mid-Continent Rift in Minnesota. I'm in Michigan. I'm actually right down here now on the edge of the rift right here. That's where I live. It's right there. Big, giant system. Duluth Complex is one part of that. That's the same scale of like the Great Dike or the Bushveld right here. We look at the, you know, the main kind of copper nickel mineralized zones in the Duluth Complex known today. It continues on the whole way, but these are actually been drilled out with resources. There they are. I've done most of my work in South Kawishiwi Intrusion, Partis River right here. That's the same scale of Sudbury right here, Stillwater, Scaregar, Changa, Dintuan, Boise Bay, Norells kind of. So these are all kind of, well, these are tiny things in here, but they have similar kind of scales. We'll just say that, of, you know, subunits of this kind of thing. So Duluth Complex kind of, you know, the ores, they're essentially, most of them are disseminated. And the magmas are true, this crystal rich slurry. I mean, here's some facts. Most Duluth Complex copper nickel ores are disseminated. Such mineralization, at least in the South Kawishiwi Intrusion, seemingly everywhere at a grade of about 0.5 copper, 0.2 nickel, half a gram total precious metals. That's platinum, palladium, gold. And there are zones of massive sulfide at or below the base. And it all depends on the magma flow where these things are. And we can track these kind of things. Why is this so? You know, well, it intruded as a slurry. Therefore, in the big scale, magmatic slurry flows homogenizes it on the large scale. That's where you get this bulk kind of thing in there. The sulfide droplets stick to plage and olivine phenocrysts and can't fall to the bottom. And that's why we form disseminated ores in there. But incorporation of footwall granitoid melts from beneath the main magma flow channels. And that's another thing, we've actually defined flow channels. How do you make a sill? Well, you have to fill it, and fill certain areas. You can heat up things below, melt that, induce new sulfide miscibility, because these magmas are intruding with immiscible sulfide droplets in them. They're super saturated in sulfur. They're carrying liquid sulfide. So if you tweak that magma by adding silica to it, you will drop out the sulfur that's actually entrained, you know, dissolved in the magma. And you can make new sulfides in there, and those sulfides are always nickel cobalt rich. And I'll show you an example of that in here. Just a geology map, simple one right here. Main kind of mineralized zone, South Kawishiwi Intrusion, Partis River Intrusion. There's some main differences. This is Archean granite right here, really quartz monzonite, giant springs batholith, where to the south, most of the Partis River Intrusion, the footwall is Paleoproterozoic sedimentary rocks, and really a very sulfidic argillite, essentially, on the Bowabic Iron Formation, Virginia Formation on top of that. That's actually the darker brown is Bowabic Iron Formation. These are huge iron mines you're seeing right here, these pits you're seeing right here. And argillites on top of that. And so you induce new sulfide, saturation when these magmas hit that. But what you're forming there is almost all pyrrhotite. So so a lot of the companies that are working here don't really even want to touch the bottom of the kind of mineralized zone, because it's just massive, replacing massive pyrrhotite. it has no value and it forms a lot of acid. So I'm going to show, some resource numbers, and they're from these red areas where there's actually Ni 43101 resources, kind of Maturi Southwest, Birch Lake, Serpentine, Saba, North Met, Wet Legs, and Wyman Creek. You might have heard about twin metals. They actually have these deposits in here. There's Tech and Polymet joined forces form New Range Copper, and they have Masaba and North Met, these two deposits here. And these are just kind of, they've been known for a long, Bear Creek, drilled them out in the 50s and 60s, a long time ago, and really no other work's been done. What's in these red areas and the yellow areas they're all mineralized. There's just no resources. There's drill holes in there, and they're, essentially every one hits mineralization, but nobody's ever put like resource numbers. But in those red areas, there's, these are from, this is in situ values. This has nothing to do with mining or anything else. This is what you can calculate from the Ni 43101 mineral resource estimates. 85 billion pounds of copper, 26 billion pounds of nickel, and you just go on through. This is metal things here. And this value goes up over a trillion, back down, over a trillion, back down. But it has a whole bunch of these, of the U.S., from the USGS critical mineral list. We're not even talking about the, titanium deposits, vanadium deposits in there. They're very different. They're oxide deposits, but this is the area that I've mostly worked. The South Kawishiwi Intrusion of the Duluth Complex. We've actually mapped out the feeder dike through this. The magmas came up from depth to here on an off-axis rift of the main mid-continent rift coming in there, and coming up, going horizontally through the Nickel Lake Macrodite. We know that through anisotropy magnetic susceptibility measurements. We actually know the direction of magma flow in that, and it went into a much larger area and lifted things out of the way, lifted most things out of the way. There's a huge block of early Duluth Complex North Acidic series rocks in here. Twin Metals' main deposit is essentially under this thing and exits it right here. Played a huge role in kind of upgrading the resources there because we actually had another geometry issue going on with that magma. And, one of the things we always, you have to think about when you think of mafic systems is sulfur saturation. Where did it take place? One thing we know in the Duluth complex, it took place before it got to where it is today. We know these magmas included carrying liquid sulfide. We see it everywhere. We see it in the feeder dike in there. So where did that sulfide, sulfur saturation take place? We look at, this is the Bald Eagle Intrusion. Back one. It's kind of shaped like this from gravity modeling. It's this huge bowl-shaped kind of intrusion, trapdoor kind of thing, with big, giant gravity anomalies right here. 3 of them right up in here and here and up here. Those gravity anomalies look like this. The one can envision, what is this right here? Well, this is where, basalt lava flows. That's part of the mid-continent rift. Sulfidic Virginia Formation, the Boabic Iron Formation, which we know are exposed down here, but we also know they're north of this area, northeast of this area, because there are huge xenoliths of them and other intrusions of the Duluth complex. That's where they are at depth. Those rocks dip down somewhere in here. So these magmas that are coming up, and there's good isotopic work that the source of the magmas for the mid-continent rift started about 140 kilometers down, and they rose up through the upper mantle into the continental crust, rose up through the Archean continental crust in here, mostly granitoids in this area, and then the idea is they would come in contact with the first bedded rock, the Paleoproterozoic rocks that come there, and which is the Boabic Iron Formation and the Virginia Formation. We know this is very sulfidic from outcrop. This is where these intrusions that are now coming out of this system right here, bring in these sulfides into the South Kawishiwi Intrusion. And it's like 5 or 6 billion tons of mineralized rock that we know there, coming out of things like these. And these might be where these are, right? We don't really know, but that's what we think. So Duluth complex initial conditions, this is what I envision in here. It's maybe 30% solids, probably not that much, but whatever, you can just make a call, right? It's basaltic magma with this array of elements in it. There's plagioclase phenocryst in there, and there's olivine phenocryst in there. There's liquid sulfide in there, and there's actually liquid oxide in there too. You take all these, mix them via shear and multiple events, and you get rocks like this. There's a big plage phenocryst right there, another one right there. This is all fine-grained olivine. There's a patch that's different right there. That's mostly plagioclase in there. You can see it's very textured. Here's some iron oxide we're seeing in there. In outcrop, these things can look like this. It's like, oh God, you know, it's like, what would that look like in core? Here we can see these are actually xenoliths, you know, or autoliths of itself. You know, you would never see that in core. That, you know, that's a chunk of that, but it's broken up because we have, you know, for filter pressed all the olivine up here. So this nickel-like macrodite, you know, we've done some drilling in there. And what do we see at depth of this thing are like Virginia Formation xenoliths. These are these, you know, go back. We see like these things right here, down here, some of them are 100 meters across, right? You know, they're giant things, right? You know, and they drilled right through them. There's a whole bunch of them in there. We see them in outcrop along the edges too. We also see in outcrop the Wabash iron formation chunks. Some of them are, to be honest, they're 400 meters long, and it's like vertical. They're imbricated vertical in this horizontal flow thing. That's, I don't know if you can see on my pointing on my map here, that's 400-meter long Wabash iron formation chunk, and it's in there vertical. There's closest iron formation is about 15 miles away from there. So how did it get there? It rose up through this kind of system in here. That's what we think, right? You know, so the main kind of mineralized intrusion is out in here. Yeah, there's mineralization in here, but it's not, you know, spruce road deposits coming in here. And this is kind of what we see. And if you, this was an early slide before kind of came up with a lot of things, right? You know, a lot of ideas. This was just, you know, the first drilling, you know, kind of a twin metals area. This is with Duluth metals at the time. Just ICP analysis, you know, ICP, weight percent iron, magnesium, whatever were used, right? You know, but we can still use that data. It's not like MgO, but we can recalculate that. But just as a proxy for all of them, you know. And this is what a classic profile looks. This is what all kinds of these things. It might have multiple kind of lobes of these in here. So this is just essentially, this is a classic slurry texture right here. We have olivine entrained in the magma flowing, and you know the whole thing solidifies in the end. So you end up, you know, and these slurries of crystals ride on liquid top, liquid bottom. So there's no olivine phenocryst up here, and there are none down in there. And just kind of a classic profile right there. We've come up with a lot more work and a lot more drilling with a kind of a three-stage component of how mineralization formed, at least in the South Kawishiwi Intrusion. We have like a barren, stage one barren top. This was just like the cracking front. You know, we actually saw it. We see it in the top and the bottom in places, just like we saw in Antarctica when you're like way far away. You have to actually make an intrusion somehow. And what always comes in first is liquid, and it's just chilling all the time. That's just, you know, splitting things up. And then we started to get into the main kind of slurry stuff in here. This stuff right here is, you know, stage 2, we called it. It's full of xenoliths of the Wabash iron formation and Virginia formation in there. It's got copper, nickel, it's got essentially pretty low precious metals. And then the main kind of stage comes in right here, stage 3. Yeah, we see xenoliths of this and this in there, but not very many. But much higher copper and nickel grades. The PGE grades go way higher because we're actually, these magmas probably stayed longer in these staging chambers and actually the platinum could partition into these sulfide droplets that are just forming right there and then being driven away kind of thing. So to come up with a lot of this, we used principal component analysis and, you know, could really see sulfide mineralization. There you go. There's 65,000 analyses on here. This is a very interesting way to look at geochemistry. We see various groups of elements. This is interstitial augite and iron oxides, footwall contamination kind of things. And the, you know, components are, you know, positive or negative. We can plot every one of these as assays down the hole. Component 1, component 2, and we see component 1 is positive in here. That's telling us we either have, these are positive, you know, the augite or this sulfide bearing. There you go. These are both sulfide bearing. We can, or at least sulfide bearing. Component 2, and this one is positive in here. So that's right here. So that's really probably all the sulfide in there. So stage 3, we see very strongly positive of both of component 1 and component 2. Stage 2 mineralization, it's got copper, it's got nickel, it's got lower grade platinum and palladium. Generally, component 2 goes somewhat negative in there. So we're seeing a lot more of essentially interstitial iron titanium and iron titanium oxides and augite. That's what we're seeing. And when we showed this to the consultants, they actually finally agreed that we knew what we were doing. If you make a box plot, we'll believe you, kind of thing. So, but whatever. But this is kind of what we think is going on. We have an earlier phase. This is like the liquid stage coming in. This is the hanging wall, the northocite footwall granite. Then the next big pulse comes through in here, much more aggressive. It's got phenocryst, it's got sulfides in it, it's got some olivine, phenocryst, plastinus, and it's got xenoliths of the sidewall, the hanging wall, the footwall. It's got Virginia formation, iron formation. It's got a northocite series. It's got salts that are on at depth too coming up, and then the main stage comes through right here, just ripping through all of this. And when this material hits the footwall, we actually commonly melt the footwall to form nickel cobalt rich zones here, because we're essentially below the phenocryst right here, so we can exalt new sulfides out. These things can actually look like this. So here's your classic Duluth Complex, not really seen much, 95 feet of 0.5% copper, 0.24 nickel, a little bit of cobalt in there. Then right at the base right here, 21 feet of 0.76 copper, that's nothing but 4.7% nickel, 0.15% cobalt. Well, that's like really interesting, and then partially melted footwall in here. So just about done here. And outcrop, a lot of these slurry things look like. This would be an extreme example of a kind of an autolith rich basal mineralized zone. So all the dark you're seeing in here is olivine, and it's essentially filtered. This area is being caked by essentially autoliths. These are intrusions or xenoliths of troctolite from the intrusion itself, and they're stacking up in certain areas because the geometry of the hanging wall might be closing things in, and the magma's pushing through, and just all the olivine gets stuck in there. And it's incredible outcrops. And yeah, you can see that's a xenolith right there. Look at the coarser grain size. That's probably a stage 1, fine grain chilled troctolite right there. Yeah, and there's another one right there. So we're getting the whole combo platter of what we see in outcrop in here. And put a drill hole through there, you would never you wouldn't envision this at all. What you can see. I think this is about my last slide. And what we've done in the in the Duluth complex in certain areas is actually take all these ideas and use that to create a coherent geology map that actually, so several decades of work in the end. And this outcrop, this map's got probably 20,000 outcrops mapped, and so the dark spots in there, and all documented. But the different stages of mineralization, that's stage 1 right there. This orange is stage 2 we're seeing. So we know there, you can see all the xenoliths. You can actually see them in there. And stage 3 is coming out at depth right here, and which goes all the way under. Oh, it's a huge area. So I think that might be my last slide. It is. So thank you. Big Rock Exploration. Just our motto is explore and discover. So I'll leave it there and see what happens.
That was brilliant. Thank you. Those images that you've taken from Antarctica are just absolutely incredible. I really, really want to go now.